All right, so I want to start off like we always do, which is offering up the question, how's the homework going? Anything that we've talked about so far that we need to discuss a little bit more? Is there anything you want to look at?
In all honesty, it seems pretty straightforward. Just trying to remember how to do partial derivatives, I guess, and remembering domain restrictions.
Right, trying to bring all that stuff back from calculus. But
hey, Bruce, I had a question. As far as the answer goes, do we have to write an actual interval? I know we kind of talked about it earlier, but just want to clarify again. Do we have to write an actual interval, or can we just say like X can't be this, Y can't be that?
So it kind of depends on how the question is worded and what it's asking. If they give you like an initial value problem, and then like they'll say something like give the interval where that solution is good, then you definitely do want to write it as an interval, and you want to look left and right of that initial condition. And that will designate what that interval is. If it's just one of those where it says determine, you know, the values of X naught, Y naught, where we're guaranteed a unique solution or something like that, then especially if there are lots of issue spots, you know, like that one you and I were talking about earlier today, Mikey, in office hour, that had like the sign of Y. And so there were a bunch of Y values that were a problem. That one I would really just say, you know, we're good anywhere Y does not equal n pi or whatever. So it kind of depends on the phrasing of the question. You know, for me, I'm really just going to be looking at, do you understand the idea? Are you getting at what it needs to be? So I'm not going to be super picky about that. Right. And so pretty much as long as you're getting the information across that you've found the correct problem spots to avoid, then I'll be happy.
Cool. Perfect.
All right. Any other questions on the homework? Cool. All right. So today we're going to look at another type of differential equation that has yet another process for solving it. And like I said, get used to this. This is kind of how DiffyQs goes. So today we're going to look at ones that are called exact. So let me go to the board and show you some stuff here. All right. So we're going to talk about exact equations. And this would be exact differential equations, obviously. But exact equations have a form that's always the same. And what they look like, we say that an equation is exact if it can be written in the form f sub x of xy, so the partial with respect to x of some function f, times that dx, and then adding to that an f sub y of xy, dy, and then equals 0. So anything that can be written in this form is what we call exact. So there's some function big F, whose partials are going to be what we're multiplying to the dx and the dy. All right, so that's what it means for it to be exact. If we have this, then the solution, at least an implicit form of the solution, so it's right here, implicit solution, is going to be whatever that function f of xy was, and that's going to equal c, where c is an arbitrary constant. So I'm just curious, is that familiar looking to anybody? Kind of remember where we did something like that once upon a time?
Is that conic sections?
Not conic sections. But think about this. So we're looking for something, for some function, knowing its partials with respect to x and y. So Thea, I don't know if you're trying to talk, but we can't hear you. Still can't hear you.
Just send it in the chat box.
Okay, so Thea just put something in there about the gradient. And yeah, you saw this or something similar to this when we were talking about the gradient. So the gradient of a function was formed, it was the vector that was formed by finding the partials and putting those in as the components. And sometimes it was we were given the gradient and we wanted to find the original field. And so we called that a potential function. And where we really use that a lot in vector calc was when we were doing like line integrals, specifically when we had a conservative field. So if we had a conservative field, the gradient gave us a potential function, and then we could use the fundamental theorem of line integrals that let us plug in the beginning and ending points. So kind of remember that? We can hear you now, Thea, by the way.
God dang it. Yeah.
Okay, so you did this before in a very different context, but it's really coming from the same place. So let me go back to the board real quick.
So if you look at this, this is exactly the form of the gradient. You may not remember that, but if you were to go back and look at your notes from wherever that was in the calculus sequence, right, Calc 3 or 4 or 2 or wherever it was, you'll see this exact form when we talked about that. And so this guy F, this is our potential function. I just realized I was using a different mic and it was sounding like crap. So hopefully this sounds a little bit better. But anyway, so we're finding that potential function and we just set it equal to C, and that's going to be an implicit solution to this form of differential equation. All right, so let me give you an example. Let me just show you how this plays out. So let's say we have this guy. We'll take 3x squared dx plus sine of y dy, and that's going to equal 0. So what we'd be looking for is a function whose partial with respect to x is 3x squared, and whose partial with respect to y is sine of y. So the way that we did this is we individually integrated the two pieces. So we're going to take that 3x squared and integrate it with respect to dx. That gives us an x cubed. So we know whatever that function f is, it's going to have in it an x cubed. Because when we take a partial with respect to x, that gives us 3x squared. Excuse me. So then similarly, we can integrate the other piece with respect to y. So I have the integral of sine of y dy, which is going to give us a minus cosine of y. And so we know that is going to be part of it as well. And the reason that it's fine just to put these two together is that when we take partial derivatives, recall that when one of the all the variables that are not the one that we're interested in are treated as constants. So like when we differentiate this with respect to x, that cosine of y goes away because it's constant in terms of x. And similarly, if we differentiate with respect to y, the x cubed goes away. So there would be the potential function for this exact equation, which means the solutions to this are x cubed minus cosine y equals c. And so you can think of each of those integrals should have had a plus c, but then if we combine them, we're adding two arbitrary constants, it becomes yet another arbitrary constant. And of course, when we differentiate that, it goes to 0, so we can just lump it all into 1. So this is what the solutions are going to look like. If we had an initial value problem, we plug those values in and we get our C. But all the solutions are going to have this form. And we could go ahead and get an explicit form for it if we wanted. Like this one's not terrible. Move the cosine of y over, and then we'd have to do an inverse cosine. But of course, if we do an inverse cosine, then we have the potential issues of domain problems. So probably better just to leave it like this until we're given a C, and then we could find the specific one. All right, so that's what the process is. That's how we're going to go about this. Is we're just going to find that potential function, and that will give us our solution. But what we probably also want to know is how can we tell if it's actually exact?
So another question for class. Do you remember how to tell if there was a potential function? Oh, look at that. Brennan's already like on top of this. He just put it in the chat. We need partials to be equal to each other to proceed. Okay, yeah, so there was this thing when we wanted to check to see if a field was actually conservative. We looked at the partials of m and n, where m and n are those multipliers of dx and dy. So we're going to use exactly that. I really like exact differential equations because it's exactly what you did back in the day when you were finding potential functions. So we're not learning anything new. We're just applying it to a different thing, and this is a pretty easy process. So let me remind you about that, but good job, Brendan, remembering what we need to look for.
So this is what it looks like if we generalize it. If instead we write this as m times dx plus n times dy equals 0. So m and n, those are just functions. Those are whatever we're multiplying to the dx and dy. But we know that it's going to be exact and it's going to work. So let me put here that we got a potential function exists. And this is an if and only if, right? So this is a huge, they go together. But it's if and only if the my equals nx. So if you take a partial of the first bit with respect to y and a partial with respect to x of the second piece, those have to be equal. In terms of the potential function itself, this guy is fxy, because remember m is a partial with respect to x, but then we're going with respect to y. And then the n, this is actually fyx. And I don't know if you remember from back when you learned partial derivatives, but this was one of the things that we saw was true about nice functions. And I'll put air quotes, nice function, was that their mixed partials were equal. And so for any of the things that we're going to deal with, they are going to be the quote unquote nice functions. And so this is going to be our check. So you can actually see that if we go back to the one that we had, right, we had 3x squared dx, and the other piece was the sine of y dy. So now if we do my, that's the derivative of 3x squared with respect to y, and that's going to be 0. And then similarly, if we do nx, n is the sine of y, and if we differentiate that with respect to x, we also get 0. So since those were equal, we know we have a potential function, and we were able to find it, right? We were able just to find it. We didn't actually have to do this check, but it's not going to always be obvious. And so we still need to go through this check sometime. So let's try another one here, and let's see if it works. And if so, let's actually find the solution. In fact, we'll do a few. Some of these are going to work. Some of these are not. And for those that do work, we'll go ahead and find our solution. So let's try this one. Let's say we've got y over x plus 6x, and that's going to be times dx. And then we're going to add to that the natural log of x minus 2 times dy, set that equal to 0. So there's a differential equation. So the question is that exact? All right, so we're going to look at my and nx and see if those things are equal. All right, well, my, we've got y over x. So the x is a constant. So differentiating the y is going to give us 1. So we get 1 over x. The 6x goes away. So that's just 1 over x. And if we look on the other side, we're going to do nx. Well, the derivative of natural log is 1 over x. The minus 2, of course, goes away. And so we see that these are equal, which means this is an exact differential equation. So let's find the solution now. Let's find that function. So what we need to do is we need to integrate this first piece with respect to x. So the y is constant. 1 over x is going to give us natural log. So we're going to get y times the natural log of x. The 6x is going to give us a 3x squared. So there's the integral of the first piece with respect to x. Now when we jump to the other side and integrate with respect to y, notice that these are all constant with respect to y. So if we put that times y, we're going to get a y times natural log of x, which is already here. So we're going to leave it alone. But then we also need a minus 2y. And then we throw on our arbitrary constant. And so there's the solution to this one. Okay, so how about we do one more like this, see what happens. So we'll just put it here to separate it. What if we had 2x plus 4y? That's going to be times our dx. And then we're going to add to that 2x minus 2y, dy equals 0. So same question, is this thing exact? And if it is, let's get the solution. So we'll look at our my. My here is going to equal 4. And x is equal to 2. So since those two are not the same, then we know that this thing is not exact. All right, so does that actually mean that there's no solution? Not necessarily. It just means we can't approach it the way that we're approaching the exacts. All right, so how about one more here? Because we're not usually given it in this kind of form, right? Think about all the differential equations that we've seen so far. How often do we actually write them as something times dx plus something times dy? The answer to that is never, right? You think about all the rest of them you've seen, they've got their y primes and the y's and all that good stuff. And so we still need to be able to attack that kind. So let me show you how we change a given differential equation so that it looks like this form, so we can figure out what the m and the n are, so that we can do this check to see. So here's an example. Let's say we've got y prime is equal to, let's go, x minus 3y over 3x minus 2y. So there's a differential equation. It is absolutely not linear. So we know we can't use the linear tricks. Ooh, but anybody see something we could do with this? Something
Couldn't you like multiply the denominator onto both sides and then separate the prime into dy and dx and then go from there and make ins the form.
Okay, so you're right. And that's what we're going to do. We're going to take this thing and split it exactly like you're talking about, Thea. But where I'm going is there's a technique we learned last time.
Yeah, it's that U sub thing of the Y over X.
Yep, that's exactly right. This is one that we call homogeneous nonlinear. Remember that horrible phrase, homogeneous?
Right. That's the one that homogeneous can mean multiple things. But in the context of this, it means that we can write the derivative in terms of y over x. So this is one of those where if we divided everything by x in that fraction, it would turn it into a homogeneous form that we could then make the u equals, which then makes it separable and lets us find the solution. So we actually already have a way of solving this one. We have a technique we already know, but I'm going to show you that this is way faster if we recognize that it's exact.
So let's do what Thea suggested, which is split this thing up. So think of this as dy dx. So we can multiply the dx over to the other side and the bottom of this fraction over here. We're going to get 3x minus 2y times dy is equal to x minus 3y dx. But we actually need everything on one side in order for us to do this whole m and n business. So I'm going to move the dy over just because I already have a positive dx and I'd rather just leave that the way that it is. So let me do one more step here. We're going to have x minus 3y dx. I'm going to distribute that minus sign so that we get minus 3x plus 2y dy. So now that's the form for exact check. So let's see what we get. We've got my is minus 3. We've got nx is also minus 3. So we know it's exact, which means we just have to integrate. So let's get our solution here. If we integrate the first bit with respect to x, we get x squared over 2 minus 3xy. The second part, when we integrate that with respect to y, we're going to get minus 3xy, already there. The 2y is going to give us a y squared. And then we just go equals c. So there's the implicit form of the solution to this guy. And you know what I think I want to do? I want to go back and I want to kind of review that idea of the homogeneous. So let's solve this one using the technique we developed last time. We'll see that we get exactly the same thing, but you'll see why this is way faster. So let me just write this. I'm going to write this down on the bottom. Try not to erase it so that we can reference it in a little bit. But there's the solution we found to this differential equation. All right, so review from last time. What we're going to do is we're going to start by trying to get y over x's. So I'm going to multiply top and bottom of this by 1 over x. So this turns into y prime equals 1 minus 3 times y over x over 3 minus 2 times y over x. And then at this point, we proceed to change the y over x. We go with u equaling y over x. So we get 1 minus 3u over 3 minus 2u. But we also have to change the y prime. Do you remember what that looks like?
Is it like u prime times y or something?
Okay, that's very close. And if you ever need to try to get it and you don't remember, rewrite this for y. So y is equal to u times x, and then differentiate that. Use the product rule. So we get u prime times x plus u. So you were close, Mike. You were on the right track.
Thanks, I appreciate it.
X, y, close enough, right? So this then is u prime x plus u. So we can subtract that u over. So we get u prime x is equal to 1 minus 3u over 3 minus 2u minus u. So we have to get a common denominator on that. So we get u prime x is equal to 1 minus 6u plus 2u squared over 3 minus 2u. And then we can separate. So we get, I'm going to have to flip this stuff over to bring it over. So I get 3 minus 2u over 1 minus 6u plus 2u squared du. And that's going to equal 1 over x. dx. Okay, well, that got us to a point where this is separated, and now we have to integrate. Well, the right side's easy. The integral of 1 over x is just the natural log of x. What about the other side? What are we going to have to do there?
Complete the square, right? To factor the denominator?
Okay, so you want to go to the partial fractions idea. Okay, maybe you don't want to go
No.
that way, but but you're thinking that's what you need.
I don't see substitution working out.
Okay.
Yeah.
Well, check it out. If you were going to do substitution,
I feel like maybe.
what we would do is we would substitute for the bottom.
Yeah.
If you look at the derivative of that, you're going to get 4u minus 6, which is a multiple.
Yeah,
Oh.
exactly. We can factor out the 2. Yeah.
So this
Damn
one's
it.
just going to give us the natural log, right? This is going to give us a natural log of the 2u squared minus 6u plus 1. We're still not quite right, though, because remember, for the derivative of natural log, you get the derivative of what's inside, which is minus 2 times this. So we actually need a minus 1/2. So we have minus 1/2 natural log of all that stuff. That's going to equal the natural log of x. And we'll go ahead and put our plus c over there.
Hey, Bruce.
Hey, what?
Maybe I lost it, but shouldn't there have been a 2 somewhere there from the U sub?
This 2 right here?
I was actually, yeah.
Yeah,
I
so
thought it
I'm
was supposed to be on
dividing
top.
by 2
Never mind.
because the derivative of this is double what I actually
Okay.
want.
Cool.
All right, so before I run the hook and convert this to exponential, let's get rid of that minus 1/2, multiply everything by minus 2. So we're going to get the natural log of 2u squared minus 6u plus 1 equals negative 2 natural log of x. And again, plus c, it's a new plus c. It's the new c times negative 2, but it's still arbitrary constant. And so then we can go ahead and run the hook. We get 2u squared minus 6u plus 1 is equal to e to the minus 2 natural log of x plus c. which will be 2u squared minus 6u plus 1 equals c x to the minus 2. So again, it's a new c, but it's still an arbitrary constant. And then the x to the minus 2, that minus 2, we bring that in as an exponent, and then e and natural log cancel. All right, but we're still not done. Because what do we have to do at this point?
Substitute back in.
Yep, got to put those y over x's back in here. I think I've already convinced you how much nicer it is just to use the exactness if you got it. But nah, we're already here, so let's finish this sucker off. So we've got 2 times y over x squared minus 6 times y over x plus 1 equals c over x squared. So we have 2y squared over x squared minus 6y over x plus 1 equals c over x squared. Let's multiply everything by x squared to get rid of those fractions. So we now have 2y squared minus 6xy plus x squared equals c. And hopefully you can see how these are the same. The only difference here is that we've got the x squared over 2. So if we were to multiply this bottom one by 2, we get the one on top. So it's good to know that the two methods brought us to the same thing. That helps convince you that this exact thing works. But hopefully this example shows you that you absolutely want to check for exact. Always.
Because if you notice that it's exact, it's going to be way faster because all it requires is 2 integrations, right? You do the one integral with respect to x, the other one with respect to y, and you're done. You think about what we just did here with this, noticing that it was a homogeneous nonlinear. Man, there were substitutions. There were still 2 integrals, but then it was algebra nonsense. And that's what we actually get away from if we notice that it's exact. There's no algebra, right? Go back and look at how we solved this one when we did it, recognizing that it was an exact differential equation. I don't think we did a single step of algebra. And we all know that that's what makes calculus hard. It's not calculus. Calculus is easy. Differentiating is a piece of cake, right? It's all the algebra that's involved later. All right. So what do you think? You like exact? Yeah, I'm seeing some thumbs up here. Exact or beautiful. If we've got it, we're going to love it. But that's a big if, because there are plenty of times where it's not exact. But the good news, just like lots of these things as we've seen, even if they're not quite what we want, we can make them what we want. Like this, what we just did here was actually a great example. There was something that wasn't separable, but by some little trick, we could make it separable. You know, yes, it increased the amount of work we had to do, but it made it so that it was possible. And so the same kind of thing is going to happen here with exact differential equations. We might have one that's not exact, but we can make it exact with just a little tiny tweak. All right, so let me show you how that's going to proceed. But before I go there, any questions on what we just did? And I'll be happy to go back to the board if we want to talk about it. Feeling okay? All right, I will take silence as everything is all good. All right, oh, and one more thing real quick. So you notice that this was one that was non-homogeneous that was exact. There are way more non-homogeneous that aren't exact. Okay, so don't think, oh man, all that stuff from the section before, we could just do it by splitting it apart and making them exact. That's not true at all, right? In fact, it wouldn't be very hard to tweak what we had here to make it not exact. In fact, let's do this. Let's go look and see the form that we just put up, or the one that we just tried. Let's look at what would change. What could we change that would make it not exact? So let me go back to the board.
So I'm going to go ahead and put the original back up here now that we found its solution twice. So we had, actually, I'm going to need your help remembering what the numbers were. Was it x minus 3y on top? Yeah, Brandon's giving me a head nod. Thank you. So it was x minus 3y over 3x
minus 2y.
Minus 2y. Okay, thank you. All right, so this was our original. When we split it up, we had the 3x minus 2y times dy. The other side, we had x minus 3y times dx. And so when we wrote it in the form that we like, it looked like this. So what could we change about this so that this is no longer exact?
Could you add some sort of constant on the outside, potentially?
Okay, so if we were to add a constant somewhere, when you say on the outside,
Not within the parentheses that are getting multiplied by the differential chunks.
okay, so like at the very beginning.
Yeah, where it's like x minus 3y over 3x, and just add something.
Like that.
Yeah.
Okay, this will definitely throw things. If we were to just add or subtract on top or bottom, that wouldn't matter. Because if we had like a +1 here, think about where that +1 would show up. It would show up in this parenthesis, which then when we differentiate would go away. We could also completely mess this up just by changing one of these two 3's. The fact that those are the same number is what makes it so that this is exact. They're different signs because we have to move one to the other side, and that leads to a subtraction, but they're the same magnitude. So if this had been, say, x minus 4y on top, no longer exact. So a really easy tweak, something of this form, is if these coefficients are not opposites, it's not going to be exact. So that's why my comment of there are way more of these that are not exact. Now you can see why, because it's just a real special case that makes it so that it is exact. Anyway, all right, so let's talk about ones that are not exact. Is it possible to make them exact? And if so, how are we going to do that? Well, what we're going to do is the same thing we've done every other time we've run into one of those situations where it's a little bit not quite right, but we're almost there. We're going to multiply. We're going to multiply by an integrating factor. So here's what we're going to do. If this is not exact, if we've got an mdx plus ndy equals 0 that's not exact, we're going to try to make it exact by multiplying by another function. So we're going to multiply by a mu. So we're going to take a mu and we're going to multiply it to this differential equation. And what we're going to do is we're hopefully going to be able to construct mu in such a way that this thing is now exact. All right, so what is this mu going to have to look like? Right? This trick of we're going to multiply by something is great, but we need to figure out what that something is and what that something looks like. So let's think about the conditions that are going to be necessary. Right? For this to work, this means that this new thing, this mu times m, when we differentiate that with respect to y, that has to equal what we get with that new thing, the mu times n, when we differentiate it with respect to x. So I'm going to eliminate the little xy stuff. I just wanted to show you that this mu can be a function of x and y, but we're just going to write it like this now. So for this to work, we need the partial of mu m with respect to y is going to have to equal the partial of mu n with respect to x. So let's write this out. Let's use the product rule. So we get mu y m plus mu my, and that's going to have to equal mu x n plus mu nx. And I'm just going to rewrite this. I'm going to move all the ones with just mu onto one side, everything with the partials onto the other side. So we're going to get mu times my minus nx is going to equal mu xn minus mu im. So whatever mu is, it's going to have to make this true. If this thing's not true, then the mu's not going to work. Before we talk about trying to solve this, I just want to point out that the equations that are exact are a special case of this. Because think about what we know about those that are already exact. If it's already exact, what can you tell me about my minus nx?
That it's equal to 0.
Okay, so it's equal to 0. Yeah, I got a couple of people doing this with their hands. Right? It's going to equal 0. So this side is equal to 0. Well, if you think about it, what is mu? What are
Would
we
that just be
multiplying?
1?
Yeah, it's just 1. And 1, its partials with respect to x and y are both zeros. And so you get 0 equals 0, which is definitely true for this. So those that are exact are just a special case. But now the question is, what about those that are not exact? All right, well, this is a partial differential equation because we're looking for a solution mu, and we have this equation that involves its partial derivatives. So we're not going to solve that. That you're going to reserve that for when you take PDEs. So if you end up taking more math later, you'll take a class called partial differential equations, PDEs, and you'll learn how to solve something like this. So what we're going to do so that we can kind of stay in our world is we're going to look for mu that have a specific form. All right, so there are really 3 good options for us. Okay, so we're going to look for one of the following. 1, where mu is a function of x. Because if mu is a function of x, and only x, then the mu sub y is going to be 0, so that term is gone. The mu sub x, that's just a derivative with respect to x, so that's a mu prime, and this is now linear. Or sorry, not linear, it's ordinary. It's an ordinary differential equation. So that would be really good. If mu is just a function of x, we're fine. A second choice is where mu is just a function of y. So I'm going to write mu equals q of y. For the same kind of logic, right? Now the partial with respect to x goes away, so this thing's gone. And the partial with respect to y is just q prime. So either of those two forms is great, but it turns out that a third form is really good too. And that's where mu is actually a function that it's made up of x and y, but the bits of x and the bits of y, we could kind of break into two pieces. So this is the third case. Now, this one may not be as obvious why this will work, but really what it comes down to is superpositioning. I don't know if you remember, but there was a homework problem somewhere back a ways where we saw if, say, y1 was a solution to one differential equation, to one non-homogeneous, and then y2 was a solution to a different non-homogeneous, the sum of those was a solution to the sum of the two equations. Well, that's what's happening here. If you think about it, if it was just p of x, we'd be good here. If it was just q of y, we'd be good with this one. Well, this is a sum of two differential equations of the same form. So we can actually find the solutions to these two individually and then put them together. So it's kind of a workaround, but we're still pretty restricted, right? I mean, if you look at these mu's, it's either a function of x alone or a function of y alone, or a function of x and y that can be written in exactly the right way. And that's not likely. But in situations where we have this, we can multiply by that integrating factor and we'll be good. Ugh. Okay. Well, now we need to know, how do we tell? How do we tell if it's just a function of x or just a function of y, or that we can write it like this? Because if you think about it, I didn't tell you how to find mu. Here I just said mu's got to look like this. Okay, great. But what we really need is a way to find these mu's. So let's go with the example of it's a function of x alone, and let's see what has to happen. All right, so let's assume this case number one. So we're going to try mu is a function of x. So I'm just going to write it as mu of x. But let's see what has to happen with this guy mu. All right, so in this case, if we go back to that mu times my minus nx and all that, right? We had mu times my minus nx. That was equal to mu of x. So that's going to be mu prime times n. And then we're going to get minus 0 times n, right? Because the mu sub y, the partial of this with respect to y is 0. So what we're left with then is a separable differential equation. So we get my minus nx over n is equal to mu prime over mu. And then if we integrate, this gives us the natural log of mu is equal to the integral, or yeah, the integral of my minus nx over n, which then we can solve this thing for mu. And we get mu is equal to e to this integral. So we're actually going to be able to find it. We're going to be able to find it if it is only a function of x. But that means that this integral has to only be in terms of x. Can't have any y's, or else this is now a function of x and y. Well, if this is going to be only in terms of x, this integral, that means this fraction is only in terms of x. So we can put a little dx on there. And so this is what's going to happen for mu to be only in terms of x. It's that my minus nx over n is only in terms of x. So that's going to be our check for this. We're going to look at my minus nx. We're going to divide it by n. And if that's only in terms of x, then we know that it's going to work. And we know we're going to be able to find it. And in fact, that mu is just going to be e to the integral of whatever that thing. So that's going to be the check for is mu a function of y, or sorry, a function of x. And it probably doesn't surprise you that we're going to do something almost identical if instead mu is a function of y. Let me just show you what happens with that real quick. If instead we go, all right, mu is going to be a function of y. So let me write that down here because we'll keep this as our what we need to check for. So we'll call it q of y. Come back here. So we're still going to have the mu my minus nx. But on the other side, now mu prime, well, that was mu sub x. Mu sub x is going to be 0 because we're assuming it's a function of only y. And then the other one was our mu y. That's going to be mu prime. And if we do the algebra on it, there's only one thing that changes. And that's this now needs to be negative. Oh, I hate to do this to you. I botched this one. No. We're going to now have an m on the bottom instead of an n because of that. And then we have to have a minus sign. So what we're going to get now, if we do this, is e to the integral of nx minus my over m. So again, this has to be a function just of y, which means the integral has to be just in terms of y, which means this function has to be in terms of y. And that's what we're going to see here, is that this nx minus my over m is only in terms of y. So they're constructed in pretty much the same way. And really what we want to look at is the difference of xm, or sorry, my and nx. We already checked those two, right? We're going to check those for exact. If they're not equal, we're going to look at their difference and see what happens when we divide by m or n. And we're going to hope, we're going to really hope, that one of those is going to be in terms of only x or only y. I know it looks complicated. When we actually do it, it's not going to be that bad. So any questions on the derivation before we dive in? Try a couple. All right, so again, remember what we're looking for is the difference in the my and nx. And we want to see, can we divide that either by n or m and get a function only in terms of one variable? So let's try one. Let's look at this guy. We're going to have y dx plus 2x minus y e to the y dy equals 0. So the first question is that exact? So you probably want to check that anyway, right? You want to do that first, because if it's exact, we just find the potential function and we're done. So we look at this first one. Its derivative with respect to y is 1. The second one, n sub x, its partial with respect to x, is 2. And so you see that those are not equal. So this is not exact. So now we look for an integrating factor. So we're going to take the difference of these two, which is either going to give us -1 or +1. And then we're going to divide by m or by n. And what we need is for that division to be only in terms of one of the variables. So which one do we want to divide by here? M?
M for sure, because it only has y in it.
Exactly.
Meanwhile n has 2x minus y e to the y. So.
Yep, and I agree. We try to divide by this, we're not going to be able to get rid of one of the x or y. So our real option, our only option, is to try to do the one that divides by m, which is, we've got that down here on the bottom. This is for it to be just in terms of y. So let's look. So nx minus my over m is going to be 2 minus 1 over y, which is 1 over y. And we've got what we need. It's only in terms of y. So we'll put a check mark because things are looking good. So that means then if we want to find mu is going to be e to the integral of this. So e to the integral of 1 over y dy. Well, the integral of 1 over y is natural log of y. E to the natural log cancels. And so what we find for this one is that we need mu equals y. So this is good. We found a function that's only in terms of y. So now let's multiply that to the original differential equation. So our new differential equation is going to look like y squared dx plus 2xy minus y squared e to the y dy. And it's actually a really quick check here to see that this is exact. If we differentiate the first one with respect to y, we get 2y. The second one, if we differentiate with respect to x, this first term gives us a 2y, the other piece goes away. And now we have my equals nx. It's exact. And now we can find our potential function. So it was a lot of work to find the thing that we need to multiply. But now we're in that really good spot, which is just find the potential function and we're done. So the solution to this then, at least the implicit form, we integrate the first one with respect to x, that's xy squared. We then integrate the second one with respect to y. Well, this is going to give me an xy squared from that first piece, so that matches here. And then I have to integrate the minus y squared e to the y. So if you're going to do this by hand, this is going to be parts. And not only is it going to be parts, it's going to be parts that leads to more parts. So when you have a power a polynomial kind of piece. That's just going to be repeated parts. But however you end up doing it, including just throwing it into the TID9 or your favorite CAS, you get minus y squared e to the y plus 2y e to the y minus 2 e to the y. And so then we slap on an equal C, and there is your implicit form for the solution to the original differential equation.
So here's where I kind of like this process, because this is the total workaround, right? We have something that doesn't actually work. It's not what we want, and yet we make it work by multiplying by this magical mu. But it's not magical. I mean, it's coming from somewhere. But again, we're restricted because we're only getting those that are exactly the right form, right? This was special. I mean, this differential equation only worked because of the structure of M and N. If they were a little bit different, we'd have to try something new. But it's a pretty quick check, and if it works, we definitely want to use it. So let's try another one here.
So let's try this differential equation. It'll look a little bit uglier, but I promise it's not that much worse. We've got x plus 2 times the sine of y dx. And we're going to add to that x cosine y dy. All right, so let's do our check for exact. So my is going to be x plus 2 times the cosine of y. And then nx is just going to be cosine of y. Well, crap. All right, so not exact. But can we find an integrating factor that when we multiply by that turns this into exact? All right, well, let's look at the two. Let's see the two forms and see if we divide by m versus dividing by n, will one of those give us what we want? So the two things we're checking again, there's my minus nx over m. And we're also looking at nx minus my over n. So is this first one only in terms of x, or is the second one only in terms of y? Either one of those would be good. All right, well, let's look at this first one. So we're going to have x plus 2 times the cosine of y minus the cosine of y. And then we're going to divide by x cosine of y. So notice we can factor out a cosine on top. That cosine then cancels with the cosine on the bottom. So if you cancel all of that, you get x plus 2 minus 1 over x, which is x plus 1 over x. So I'm actually going to stop here because we know we're good. We've got this thing that's only in terms of x, which means that's going to find us our mu. If you were to go and do the other one, you're going to see that they don't cancel out. When you divide by the x plus 2 sine of y, you're still going to be left with a cotangent of y. And the x's don't go away.
Hey, Bruce.
Hey, what?
Is that x plus 1 over x or 1 plus 1 over x? Oh, okay.
Yeah, thanks, Maggie. So it's x plus 1, the entire x plus 1 over x. Thank you. All right, so let's get our mu. So mu then is going to be e to the integral of x plus 1 over x dx. So that fraction is the same as 1 plus 1 over x. So when we integrate that, we get x plus natural log of x. The addition means we're multiplying the two pieces. The e to the natural log of x becomes x. So we get x times e to the x. So that's what mu is going to need to look like now. So any questions on how I found mu before we multiply by it and try to find the potential function? All right, so we're going to multiply by that mu. So what we get is x times x plus 2 e to the x sine of y. And then the other piece is going to be x squared e to the x cosine of y. And this is now exact. You can check it if you want. I'm not going to bother. But you could check it and you'll see that it is exact. We know it's going to be exact because of how we constructed mu. That's kind of the whole point. All right, so now let's see if we can find our potential function. So we need to integrate this first thing with respect to x and the second thing with respect to y. I say we start with the second part. Just get the easy, it's easier, so let's just knock it out of the way. So if I integrate this with respect to y, the x squared e to the x is going to be x squared e to the x, it's a constant, and then cosine, its integral is sine. So that's the integral of the second part with respect to y. So we know the potential function is going to have that in it. All right, so then we get to integrate this thing with respect to x. Well, that's x squared plus 2x times e to the x that we need to integrate with respect to x. I'm not worrying about the sine of y because that's just going to be a constant. We'll throw that on at the end. So we have to integrate this thing, which if you're going to do it by hand, is parts. There's two sets of parts. There's the x squared e to the x and the 2x e to the x. The x squared, that's going to require parts multiple times. But whatever you do, however you get there, the integral of that is just x squared e to the x, which then we get our sine y as well. So there's the integral of the first piece with respect to x. And notice that they're actually the same. So it turns out for this one, we get x squared e to the x sine of y equals c. So like I said, it looked ugly. Turns out it's actually not that bad, at least in terms of its form. And again, this is an implicit form. The explicit form, if you solve it for y, we can definitely do that. It just brings in sine inverse, which means we're going to have to be careful. But knowing the initial conditions, if this was an initial value problem, it would allow us to find c and also tell us where we're going to be so we know what to do with that inverse sine. All right, so integrating factors. They're kind of nice when they're the right form.
But of course, I also told you there was a third form for these, right? There's the where mu is only a function of x, where mu is only a function of y, and we just did those two. The third form is when mu is actually a product of a function of x and a function of y. But I think what I'm going to do is leave that to next time, because I don't want us to get too far ahead. We're not terribly far ahead, actually. We're down to like half a section ahead, but we're keeping a good pace, so I am going to pause here. So let me just real quick stop the recording.